Welcome to the lecture of subject signal systems KEC 403, and we will be discussing types of signals in this lecture, some basic type of signals, and we will perform some numericals. So, classification of signals after signals are divided into continuous time and discrete time. The first classification is of periodic versus aperiodic signals. So, a signal is said to be periodic when a discrete time signal x of n is equal to x of n plus capital N, and this is for all n, for all time variable n, and this n, the smallest value of n, is said to be the fundamental period of the signal. Fundamental period, why fundamental? Because this is the smallest value. The multiples will obviously repeat the signal if it is a periodic signal, but it will be fundamental only if the value of n is minimum. Similarly, for a continuous time signal, we represent it by x of t is equal to x of t plus capital T. If this is so for all values of t, then this t appears to be the fundamental period of the signal. If this is not so, then the signal is aperiodic. So, just quickly taking some examples, the best examples of continuous time signals which are periodic are sinusoids. The sinusoids are sine, cos, and complex exponentials. So, e raised to the power minus j omega naught t, where this j is the imaginary number square root of 1. So, these three signals are basic signals which are sinusoids and are periodic in nature. The fundamental period of all three of them, the formulation which is written gives us 2 pi upon omega naught. So, all the three are have fundamental period of omega naught, 2 pi by omega naught. And we can of course take a modulus sign because the sign of the omega naught will not change. So, any particular example in which there is a sine, cos, or a complex exponential is always going to be periodic in nature. This is the basic example. All the other signals will be a combination of these three signals. Otherwise, other descriptions are also possible, but basically this is what is followed. Like for example, it is sine of 4t. So, the fundamental period of this signal T1 is, if we compare to the previous slide, this omega naught is 4. So, it gives me 2 pi by 4. One can write it pi by 2. Similarly, T2 is in this case the omega naught for this is 2 pi, which makes the fundamental period of this signal to be 1, and the fundamental period of the third signal, which is complex exponential, there is no value of omega naught, so it is 2 pi by omega naught, and if suppose there was a value, we will get some results. So, this is the description of signals and what are their fundamental periods. It is also possible that we define signals in composite manner. So, if we define the signals in composite manner, in that case, what we do, how do we calculate the period? We calculate T1, we calculate T2, and we take the least common multiple LCM of T1 and T2, and that will be the fundamental time period of the signal. Also, the ratio of T2 by T1 must be a rational number for the composite signal to be periodic in nature. So, like in this example, it is cos t plus sin t. The values of omega naught for both is 1, and therefore we can write that this T1 is what? 2 pi. What is this T2? Also 2 pi. So, what is the complete T? 2 pi. The LCM of the least common multiple of 2 pi with 2 pi gives me this, and the ratio remains 1, and both are equal. Therefore, the signal is periodic. It is not that it is not periodic depending on this criteria, since the ratio of the two individual fundamental periods is rational. The overall signal is periodic, and the fundamental period is 2 pi. Like for instance, we have now a composite signal which is discrete in nature. So, we will also take up this example. These signals are discrete time complex exponential signals due to the presence of j. The fundamental period evaluation for discrete time complex exponential in a similar manner. Suppose this part is omega naught, so we will write 2 pi by omega naught into m, and we will select m. So, which means we will write this at 2 pi upon the omega naught value is pi by 3, and we will select m, which means it will be 6 into m, and we'll take m is equal to 1. We'll always have n as an integer. For discrete time, the n has to be an integer. Similarly, n2. So n2, now you can understand in this case, the portion that is along with the complex exponential argument is pi by 4. So the fundamental period becomes 2 pi by 4 pi by 4 into m, which means that it is 8 for m is equal to 1. So if you select m is equal to 1, the fundamental period for the second individual signal is 8. So what is the overall n? The overall n is the LCM of n1 and n2, and this gives me 6 cross 6 and 8, so 24. The LCM, the fundamental period for discrete time signal, this n has to be an integer. That is the most important point that one has to remember. It needs to be an integer, and the evaluation process is like this. The same description will be for sine and cos for this also. So suppose that we have sine of omega naught n, or I have cos of omega naught n, then both will have a fundamental period of n is equal to 2 pi by omega naught into m. We'll select m has to be an integer. We'll select m, and the m makes the n an integer, but m has to be an integer. Both have to be integer. This is also an integer, and this has to be an integer for a discrete time system. Shifting by n gives x of n, then the n has to be an integer. So this is composite signal case for x of n. Here you can see that the ratio of n1 and n2, if we write n1 and n2, then this n1 and n2 ratio is rational, and therefore this overall signal appears to be periodic. Like in this case, if we calculate in this case, so this is a continuous time signal x of t, so we will calculate t1, and what is t1? This is 2 pi by omega naught is square root of pi, so it is 2 of square root of pi. T1 is this much seconds. What is t2? 2 pi upon 2 pi, which is 1. Before moving forward, the ratio t2 by t1 is 1 upon 2 square root pi, which is not rational. So since it is irrational, the overall signal is aperiodic. The overall signal is aperiodic. So therefore, if in case of composite signals, the individual periods are not the individual periods and their ratios are not rational, then in that case we get an aperiodic signal. Now energy signals. A signal can be an energy or a power signal, or neither energy nor power. So if signal is energy signal, if we calculate, this is for continuous time x of t. So we evaluate E infinity, limit t tends to infinity minus t2 plus t, mod xt square dt, and if this comes out to be a finite value, then the signal is said to be an energy signal, otherwise not. If E infinity tends to infinity, then we calculate the power of the signal. It is possible that aperiodic signals are energy signals, can be periodic signals, not periodic, energy signals, I beg your pardon. So can be energy signals. For sure, truncated signals are always energy signals, discrete or continuous. Energy signals, right? So this will be the formulation. We'll see and apply how to evaluate. Next is the description of power. So what is power? Power is rate of doing work. The work is stored as energy. So energy was E infinity. Now we calculate the power. So it is the same formulation, divide by total duration. The total duration in the last slide you can see was from minus t to plus t. So what is the duration? From minus t to plus t, what is the duration? The duration is 2t. So while evaluating power, we'll take the rate of doing work, rate at which the energy has been stored in a signal, and that can be evaluated by the same formulation but upon 2t. If we perform that, then we obtain the value of P infinity. If this P infinity comes out to be a finite value, then the signal is said to be a power signal. We evaluate P infinity. If it is a finite value, it is a value that we get, it does not tend to 0, then we say that the signal is a power signal. For power signals, the energy content will be infinity. Of course, we calculate first of all the energy of the signal, and if the energy is finite, then the signal is energy. In this case, the power of the energy signal will be 0, but if the energy tends to infinity, we evaluate power, and if power comes out to be a finite value, then the signal becomes power. It is also possible, a third category, that both of them tend to infinity. It is possible that both P infinity and E infinity tend to infinity. In this case, the signal is in the criteria of neither energy nor power. So we'll see some examples. This is for continuous time signals. Like suppose we can check that whether this signal is energy signal or a power signal. So what is our formulation? Our formulation is very simple, that E infinity is basically limit capital T tends to infinity minus T to plus T mod xt square. In this case, if I do that, I will get k square into e raised to the power minus 2 at dt, and also there is ut. So also there is ut. What is what does the ut does? It is 1 for positive values. So we basically have limit t tends to infinity from 0 to t. K square is a constant, and we need to only integrate minus 2 at with respect to t. So integration is very straightforward. It is e raised to the power, I can write that also. So if it is limit t tends to infinity, we have e to the power minus 2 at k square upon minus 2a, and the limits are 0 to t. When I put the limits, I get e infinity equal to, we put t tends to infinity also, we get k square by 2a. Therefore, the signal has a finite energy, the signal is an energy signal. If we obtain the power of this signal, the same signal, if you obtain the power of the signal, you can understand the power will be 0, because in the same formulation, it is basically 1 upon 2t. So when t tends to infinity, the finite upon infinity will make it 0. So the power of the energy signal is 0. Suppose a similar looking signal is k e raised to the power minus j at. Okay, due to this j, this signal is complex exponential. Signal is complex exponential. What is the energy content of the signal? The energy content of the signal is by formulation limit capital T tends to infinity minus t to plus t. We integrate the signal's magnitude of k e raised to the power minus j a t square dt. We perform the mod part. You can use Schwarz inequality also, but since it is a constant, I can take the mod for this. And what about the mod of this signal? E raised to the power minus j theta's mod, what it is? It is the mod of cos theta minus j sin theta, isn't it? What is the magnitude of this? This is the real part is cos theta, the imaginary part is minus sin theta. So the absolute value is square root of cos square theta plus minus sin square theta. So minus square becomes plus. So square root of cos square plus sin square, and this magnitude is nothing else but 1. So this magnitude apart from this is 1. So our E infinity formulation now looks like limit t tends to infinity integral from minus t to plus t k square dt. So if we integrate with respect to t, there is no function of t in the integrand itself. Therefore, I will get only the period is 2t. So what I will get? I will get limit t tends to infinity k square and 2t. This is what we will get. If we put the limit, the E infinity tends to infinity, which means the signal is not energy signal. We are not sure whether it is power or not, that we will evaluate and see. But till this time, if we put the limit t tends to infinity, since t stands here, we'll get infinity. Now we go to the calculation of power. So if we go to the calculation of power, the P infinity for the same complex exponential will be defined as 1 upon 2t and the same formulation. So we have evaluated the same formulation, and this was something like this. Now this cancels out, and therefore the P infinity appears to be K square, which is a finite value. The signal is a power signal. Since the signal is periodic, it will be a power signal. So all periodic signals in general, all periodic signals are power signals. So this is not only subject to complex exponential, it will also expand to sine and cos. So sinusoids will always be power signals. The energy content of those signals will be infinity. The signal is of infinite duration. So earlier also I discussed that the signal is truncated, then it is energy signal. So if the signal is for infinite duration, the energy content of the signal cannot be limited to a finite value, and therefore we will get something which is infinity. We'll always get something which is infinity. Now there is this signal which is k e raised to the power minus at. So if I will leave this to my audience, but if we evaluate e infinity, you can understand what is the difference from the first signal. This is of course a real exponential. There is no j. So if I evaluate limit capital T tends to infinity and we evaluate minus t to plus t mod of k e raised to the power minus at whole square dt. Since there is no ut, this will tend to infinity, and one can accurately verify the p infinity for this also tends to infinity. So which means the signal is neither energy nor power because of the absence of u of t. Just compare this with the first signal. The first signal had the component, you can see the first signal had the component of ut. In this second signal there is jt, and the third signal is still real exponential but has no ut and will give you e infinity and p infinity, both tending towards infinity. The signal is neither energy nor power. So that is the theory. Well, similar looking signals, complex exponentials, real exponentials, truncated real exponentials behave in a different manner. Okay, so this is about how we evaluate energy and power of the continuous time signals. Again, we can also evaluate the same for a cos. So how does this calculation go? So if we evaluate the energy content of the signal, the energy content will be limit capital T tends to infinity integral minus t to plus t AC square. Remember mod xt square. So in this case there is no requirement of mod, it is a real quantity. So cos square omega naught t dt. This integration cannot be performed at this stage. We'll use a trigonometric identity. So what we will do, we'll perform limit t tends to infinity. Minus t to plus t is okay. AC square is a constant. What we can do, we can use 1 plus cos 2 theta. So this is 2 omega naught t and by 2. By 2 I am taking outwards. So now if I evaluate this integral and put limits, one can understand. I'll get AC square by 2 here, since it is only 1. So I will have some integration there, but the first part will be 2t, and the second part I'm letting it suppose I. So what is I? I is basically the integration of cos is minus sign. So which this I is limit t tends to infinity minus sine of 2 omega naught t and divided by 2 omega naught, and we'll put the limits of minus t to plus t, which is going to be a finite entity. Since this is going to be a finite entity, if we put any t and substitute t tends to infinity, because t tends to infinity will not make it infinity since it is the argument of sign. This entity, the I, is finite. However, if we look at the first part, since it has this 2t component, if limit t tends to infinity, it will not give me a finite value. Since t tends to infinity, this first component will tend to infinity. So what we can do, we can now go and evaluate p infinity, which has a formulation of limit t tends to infinity 1 upon 2t. Remaining part we have evaluated. So what we have evaluated it to be AC square by 2, 2t and I, which is a finite value. So if I is a finite value and I divide it by 2t and put the limit t tends to infinity, then this is finite by infinity. The second term vanishes. The first term remains. The first term, if I use this formulation, so there is no component of t also. So I'll get p infinity of AC square by 2, which is the power content of the signal. The power content of the signal. Signal is periodic, signal is to be power. It is very simple. Also, if a similar looking AC sine omega naught t is there, then you can understand it will also be a power signal. Similarly, for this signal, you can understand since it is a complex exponential case, there is a minus j, so it is a complex exponential case. This is the phase, and phase has no magnitude since it is in conjugation with j, and therefore even if for this signal we evaluate, it will be a power signal, and as per the calculations of the previous slides, this will be 3 square, basically 9 watts. That's a complex exponential. One can verify it will be. The energy will be infinity, the power will be finite value since it is a periodic signal. This signal one can also verify if we calculate for this, E infinity will be limit t tends to infinity, integral minus t to plus t, mod 40 square, so it becomes 16t square dt, and this will be 16 upon 3 and t cube, and minus t to plus t, and the limits are also there. So we basically end up getting an infinity value. You can verify that P infinity also tends to infinity. The signal is neither even nor power, neither energy nor power. So thank you.